It's my great pleasure to introduce Eitan Grinspun, professor at Columbia. So Eitan is sort of an academic superhero. By day, he is a prolific graphics researcher. He won numerous prestigious awards, including the Popular Science Brilliant 10. But then by night, he seems always to be donning a cape and flying down to New Zealand and exotic places like that to actually work on special effects for movies. And his recent credits include Steven Spielberg's Tintin and Planet of the Apes, which had really unbelievable special effects. So I'm very much looking forward to this. Eitan.
Isn't it Tantan?
Tantan. I'm sorry.
Thank you, Adrian. I've been looking forward to visiting everyone here, and I'm enjoying my visit tremendously. So as Adrian mentioned, I got kind of pulled into graphics because of special effects. And the story that I want to say today is a little bit about how some of the work that we've been doing for visual effects has actually started leading to impact in the hard sciences, and what is the connection there between those works. So maybe a little word on the difference between how we might approach the computation of the motion of physical systems in engineering disciplines versus in visual effects. So in engineering, when we talk about modeling a physical system, we do so because usually we want that building or structure not to fail. We want it to stand up. And that's really boring, right? And so in visual effects, we're interested in things like this. Right, and I wouldn't want to be the cameraman who has to film this. So we want to do this in a virtual context. So that's a comparison between the fact that in engineering we care about solving static problems. And in fact, whenever anything interesting happens geometrically, like buckling or folding, that's a sign of failure. So usually we stop computations well in advance of when that happens. And we're just interested in asking, is something going to buckle, not how does it look like after it buckles or fails. Whereas in graphical applications, we've traditionally been interested in studying how do things buckle, how do they fail. And so we've been developing techniques over the past 2 decades that are kind of specialized to what engineers would call as post-buckling phenomena. All right? Now, the other thing that I want to say about that is that a lot of the interesting behaviors that happen that are these post-buckling phenomena are behaviors that are governed by geometry, or engineers would say by geometric nonlinearity. If you have a cylinder and you crush it, you see this sequence of diamond-shaped folds that happen. And that sequence is not determined by the fact that this is metal as opposed to plastic, as opposed to paper. It's determined purely by the geometry of this configuration. And you can see this happen for lots of different materials. So a lot of interesting deformations happen just by understanding the geometry of what's going on. And in fact, without closely matching material parameters or anything else, just by setting up a similar geometry, you can reproduce these effects in real life. In computer graphics, we're interested in these nonlinear effects due to geometry because they're the things that make nice wrinkles and swirling motions and so forth. And so we're interested because of the richness that they add in terms of visual detail. So with those things in mind, I'd like to tell you a little bit about our goals and how we approach them. So in my group, we're interested in computing the motion of physical systems. And we want to do so efficiently, so the algorithms have to run fast. We want to do so reliably in the sense that the algorithms shouldn't be fragile. If you slightly change parameters or tune them, things blow up or break down. We want to do that with an eye towards creative processes, so there are actually artists in the loop. And finally, my favorite one is we really want to look for simple algorithms. When we find simple algorithms, if we're lucky enough to do that, they tend to be more rapidly adopted. It's easier to convince people to use them. And the way that we approach simplicity, and in fact all of these criteria, is by looking for simple geometric insights. We study the geometry of the underlying problem. And I want to tell you a story about that and try to give you a sense for that. So here's a motion of the here's the motion of the planets. It's the solar system, and we can just think of as how we might simulate this, and we might write down some ordinary differential equation. We might have the force of gravity, power law, and so forth, and just plug in some discretization of this and carry this forward. This would be a very standard sort of differential algebraic sort of view of how to treat planetary orbit. Now, instead, we might approach it geometrically, and one of the pieces of geometry that can be used to describe the orbit of a planet is Kepler's second law. So here's the sun, and the ellipse is marking the motion of a planet. And Kepler's second law says that if we track the radius from the sun to the planet and measure some interval of time, and we do this at some other instant in time, and we measure the same interval in time, maybe 3 days in both cases, then the areas of these pizza wedges will be the same for equal intervals in time. So it's an invariant of this physical system is that the radius sweeps out area at a constant rate. And so that means that when the planet is far, it has to move slower, so you get long, narrow pizza wedges, and when it's nearby, it has to move faster to maintain the same rate of area sweeping. This is a very geometric view of the motion of a planet. And in fact, this geometric view of the motion of the planet was proven originally by Newton in the Principia. And what's neat about Newton's proof of this motion is if you look at it, it has a bunch of triangles, has a bunch of polygons. This is the sun, and this is the motion of the planet, and this is the direction the planet would have continued if there was no influence of gravity. But gravity pulls it towards the sun, which alters the path. And this here is parallel to this, so that's the alteration of the path. And so Newton, even though we attribute the calculus to him, if you look back at some of the early proofs, he didn't use calculus. He did it all in the discrete sense, the discrete world, and then argued that this converges as you take smaller and smaller steps. So here's a modern reproduction, just a zoom up and a cleaned up version of Newton's proof. Again, the sun, motion of the planet, where the planet would have gone in a straight line, and where it goes instead. And what's neat about this, and so Newton proved that these two triangles would have the same area if the same amount of time, h, elapses between different steps. That was his proof of Kepler's second law. And we could walk through this. We don't have time. Adrian told me I have 10 minutes less than I thought, so I'm going to skip some slides too. But we could walk through this. But it's simple high school geometry tells us that these triangles have the same area. What's neat is I can take Newton's proof and I can just relabel it with the sort of labels that we might attach to an algorithm that steps forward in time. And I can just read off from this diagram a time stepping rule. So Q are positions and P are momenta. So this updates the positions based on the momenta, and I'm assuming mass is 1 here, and it updates the momenta based on the forces. And I can say what happens if I apply this kind of time stepping rule when integrating a physical system. So here's a comparison between this algorithm, which we just read off of Newton's proof, and the standard explicit Euler, which is the simplest algorithm that we teach in Introduction to Numerical Methods for updating the position and momenta. And what we're showing here is a trace of the motion of the planet over some interval of time. And h here is the size of the time step that's used, and it's running for a long time. And one of the classic traits we know about explicit Euler is that the motion of the planet gets bigger and bigger in radius, and eventually the planet goes off to Alpha Centauri. So explicit Euler blows up. And if we use the algorithm that had Kepler's second law built into the algorithm from the ground up, literally by building it from the proof of Kepler's second law, then even though we take time steps that are 100 times bigger, so it should be less accurate, here, the dotted line shows us the expected analytical result, the elliptical orbit, and we see that the computed orbit drifts from the dotted line. So there's no free lunch here. You're not tracking the trajectory more accurately. But qualitatively, you're always retaining this elliptical nature of the orbit, and it never blows up or decay. You say, okay, that's fine, but maybe you paid more to run this algorithm, so you're getting better results. Actually, if you read both of these algorithms, they are both explicit algorithms. Neither of them requires an implicit solver. Neither of them requires more compute time. So they're equivalent in terms of the number of instructions to run. One of them just has this coarse characteristic of the physical system built in. So we can try to be inspired by this kind of idea of building geometry into our algorithms. And in a lot of the physical systems we're interested in dealing with, we're interested in modeling the motion of curves and surfaces of different kinds, hair, clothing, and so forth. And so there, we want to take whatever problem in elasticity or whatever smooth problem we have and look at it with a geometric lens. That means we're going to build a discrete picture. We're going to talk about discrete trajectories, discrete curves, surfaces represented as some collection of samples. And we're going to try to rebuild whatever geometry was originally inherent in the smooth setting and rebuild that in the discrete setting. So let me show the simplest example I can think of to guide you through that. Suppose we have, and this was a motivating example, and then I will use this to develop some algorithms later on. Suppose that I have some smooth curves on the plane. And then one thing I can do is I can define the notion of curvature at any point on the curve. So if the curve is shown in blue, and I take 3 points, PQR, on the curve, then for any 3 points I can fit a circle uniquely. All right? And if I think of moving Q towards P and moving R towards P, at any instant I can fit a circle through them uniquely. And in the limit, as Q and R all approach P, I can ask, what is the circle that I get, this limit circle? And that circle is, in some sense, the best fit circle at that point on the curve. And the radius of that circle is called the radius of curvature. And the inverse of the radius is called the curvature. And I can assign a positive or a negative sign to this curvature by saying that if I have a sense of traversal of the curve, so I'm going this way along the curve, then I can say whenever I turn right, I consider that to be negative curvature, and whenever I turn left, I consider that to be positive curvature. Now, one telltale sign that I've been really looking at the geometry here is that I never introduced a parametrization into this curve. I never had to say this is gamma of S or something like that and write down the curvature as some sort of expression in terms of derivatives of the curve with respect to some parametrization. We talked about it all in the limits of fitting circles to inscribed points. So we really are giving definitions that don't rely on the parametrization. So now we have this notion of a curvature, and it's signed, because if I turn right or left, I get opposite signs, and if I turn sharper, I get a bigger value. And we can take this a step further, and we can talk about the Gauss map. If I look at the normal vectors for each point on this curve, and I consider just the unit length normal vector, I can take that normal vector, and I can translate it to the origin. And so the tip of that normal vector, if it's a unit vector, will always land somewhere on the unit circle. So I can think of a map that takes every point on the blue curve by looking at its unit normal to some point on this green unit circle. And I can ask, as I move along this blue curve, what's the corresponding motion on the green circle? So if I have a curve that goes in a straight line, then its normal is constant. So I get a point on the unit circle. If I have a curve that goes mostly in a straight line, but then around here it suddenly makes a turn, well, the normal goes like this. So at that instant, I get this rapid movement on the green circle. In fact, you can show that the speed of movement on the green circle, if you go with unit velocity along this curve, then the speed at which you move here is the curvature. All right? So we can talk about this mapping from a curve to a point on the unit sphere, or to a curve on the unit sphere. Now what if you have a closed curve? So here at the top I've drawn a bunch of smooth closed curves, and I've looked at the corresponding mapping onto the green circle. And of course, if the original curve is a closed curve, then I'm going to complete some number of closed loops on the green circle. And I can count how many of those loops I make. So if I'm going this way, I'm just going to get a closed loop like this. If I go the other way, I'll get a closed loop like that. And I give them opposite signs, depending on whether I've gone over the green circle once in a mathematically clockwise or counterclockwise, negative or positive direction. And if I have a blue curve that goes around twice before it closes, then those might either cancel out or not cancel out on the green circle, depending on whether those directions are opposite, like in the infinity case, or not. But anyway, for every closed blue curve, I get an integer. And notice that if I wiggle this curve, that integer doesn't change. In fact, that integer is just a function of the topology of these crossings of the curve. If I wiggle the curve without changing the relative number of crossings, that integer doesn't change. The only time the integer changes is if I shrink this knot kind of moves and then pops out. So it's a topological invariant of this curve. So now, if I put all that together, I can state a very simple theorem. It's the turning number theorem. And it says that if I add up along every point on my curve the curvature, and I do this for a closed curve, then the curvature is always 2 pi times some integer. In fact, that integer is the turning number. And in fact, if you remember that the length of traversal along the unit circle is the curvature, then when you add up the curvature, you're always going to get some multiple of 2 pi, because you're always going some closed number of times around the unit circle. And again, this integral of curvature over the blue curve is a topological invariant. It only depends on the number of crossings. So that's really interesting, because this is the first example of a phenomenon that arises over and over in physics and in differential geometry. Differential geometry is just a language for describing physics, which is that there are relationships between things that seem to be local and things that are global. And this really tells you can't pick, for a closed curve, you cannot pick the curvature independently at each point on the curve, because the sum of all the curvatures around the curve has to equal something that is fixed by the topology of the curve. So we can say, suppose that for our physical system, this is the object of interest. Adrian?
Can we go, does it work in the other direction as well? Does that prove that the curve is closed?
Yes. Yes. So, so suppose now we say this is the property of interest. Then the way we would approach our research is to say, now we're working with discrete curves, and the game we want to play is to make sure that that property is preserved for discrete curves. So one way that we might define curvatures, we might say now we have this discrete curve, and along every line, well, nothing interesting is happening. And when we get to a vertex, we have some turn by some angle alpha. And we can assign a positive or negative number to that alpha, as we did before. And so we can just say that the total signed curvature is just the sum of these signed angles. That seems like one possible definition for the total curvature. And now we can say what happens on the unit circle. So we can say, OK, whenever we go along a straight edge, well, the normal is constant. So I just get a point on the unit circle. An edge maps to a point. And whenever I'm at a vertex, well, the normal is changing from the normal at one edge to the normal on the next. So each vertex maps to an arc on the unit circle. So there's a nice primal dual thing of points in the primal picture mapping to edges, if you want, on the dual picture, and edges on the primal picture mapping to points on the dual picture. So you can look at all of this. And again, we could go through the whole thing we did before. But here's the main result, which is something you learned in high school. The sum of exterior angles of a polygon is 2 pi. Okay? And you can generalize this to say that for any polygon, even a more complex one that wraps around itself more than once, the sum of the angles is some integer multiple of 2 pi. So really what I'm telling you is that if the turning number theorem, as I talked about it in the smooth case, seemed mysterious and interesting, in the discrete case you already know how to prove it, right? And for this choice of curvature, namely assigned angle at each vertex, we can write down the turning number theorem exactly for an arbitrary coarse polygon. And this should be distinguished from something that is typically taught and analyzed in the finite element world. In the finite element world, we talk about discretizations by saying, in the limit, as we refine our mesh, as we take smaller and smaller time steps, as we throw more and more computation at our problem, do we recover the solution in the limit? And this is saying for an arbitrary polygon, no matter how coarse, do we preserve this theorem exactly? So we've built in some theorem. Now what's interesting to note is that there are in the smooth world, there are many interesting properties pertaining to curvature on a smooth curve. And I've just chosen to talk about one of them, which is the turning number theorem. Turns out that if you pick one of your other favorite properties, for example, properties associated to soap bubbles, you get different theorems associated to curvature that are not satisfied by this definition of curvature. So depending on what geometric structure you start with, you actually end up with different definitions for what your discrete objects should be. Okay. That's the math part of this talk. And that's kind of the setup for how we approach these problems. Let me walk you through a real-life example of how we might apply this. So here is a video that a physicist friend of mine from the Jussieu, the University of Paris #6, sent to me, in which he takes an elastic rod, namely any sort of flexible curve, a strand if you want, and he ties it up and starts twisting it. And depending which way he starts with the same knot, and depending which way he twists it, he gets a different shape that forms. And that shape that's formed is dominated by geometric properties. I can get that shape to form with a wide variety of different materials, wide variety of silicons and rubbers and metals. And in particular, this shape is governed by the resistance of the curve to bending, the resistance of the curve to twisting, and the fact that the curve can't go through itself.
Eitan, is this assuming that the material is homogeneous in some way?
Yeah. So of course, as soon as you introduce things that break symmetry, that make the material not homogeneous, then you will get distortions to this, right? But for any material, whether it's this one or this one, the geometry will be basically the same, and you'll get the same sort of patterns forming. So what's going on? What's the model that we need to model this? Well, we have this curve, and clearly we need to model the position of this curve in space, all right? But modeling the position of this curve in space is not a full picture, because here's the curve and here's the curve. Okay, modulo the vibrations, which I didn't intend to put in there, these are clearly different configurations of the physical material, but the material is in the same points in space if you just think of a curve. So we really also need to think of the flesh sitting around this curve. And the analogy that I like to think of is the children's toy that has the metal wire and the beads that you can slide along this wire. Okay, so the beads represent the flesh, and then the metal wire represents its position in 3D. And think of stuffing this toy. It's not as fun for a kid anymore, but think of stuffing it with so many beads that the beads can't slide around anymore, but they can still roll around. All right? So then the rolling around of each bead represents the fact that I can turn this cross section. It can turn in place. Just looking at the top, this thing, it can turn in place. So that's the rotation of the beads. And mathematically, what we say is that we have a framed curve. We have a curve, and at each point on the curve, we associate some 3D frame. All right? And that frame is going to be an adapted frame. So it has 3 vectors, all perpendicular, and one of them lines up to the tangent of the curve. And now we're going to write down the energy as this thing is deformed as a sum of the bending and twisting energy. And the twisting energy is essentially going to be the angular momentum of this frame as it goes around the curve. So it's going to measure the rate at which the frame rotates about the tangent as it proceeds along the curve. So if I start out with this in a straight line, then the frame is just going to look like this, and there's no twisting. But if I apply a twist to this, then the frame is going to move like this. So this rate of turning of the frame about the tangent vector, that's going to be this twisting. And you can see it here. It's how much does one of the vectors change in the direction of its perpendicular vector. That's measured there. So a natural thing we can ask is, if I position this curve in space and I somehow manage to get it to hold fixed in space, but I don't apply any clamped boundary conditions that stop the frame from rotating, then how will the cross sections align themselves? How will they most relax? Right? In the case of the children's game, that would amount to saying you set the position of the metal wire, and there's some amount of glue between the beads that prevents them, so they kind of resist turning relative to each other. And now the beads are free to rotate about the wire, but the wire is fixed in place. So clearly, the frame has to rotate by some amount just to follow the wire, but it should avoid turning as much as possible. It should have the smallest amount of angular momentum. And so you get this kind of twist-free frame shown here. It's kind of moving just enough to follow the wire, but not turning any more than it needs to. So you can summarize the requirements for this twist-free frame as saying there's no rotation at any instant about the tangent vector, but there's just enough rotation to keep the tangent vector following the curve. Interestingly, and now we're going to go back to the little example we showed before. Remember that before we talked about mapping every point on the curve to a point on the green circle. Interestingly, Kirchhoff, and this is the same Kirchhoff from electrical circuits, introduced a famous analogy between elastic rods and spinning tops, dreidels. And he said, if you consider a statics problem for an elastic rod, there is a corresponding dynamics problem for a spinning dreidel or a spinning top. And in particular, the length along the rod corresponds to the time dimension as the spinning top spins. And the tangent vector along the rod corresponds to the main axis that's precessing, along which the spinning top is oriented. And the twisting, or the material frame, this frame that we drew on the rod, well, that corresponds to the actual frame of the spinning top that's spinning about its central axis. All right? Now, what's nice about that analogy is it gives us a mapping from this curve to the unit sphere. Because if the tangent vector on this curve corresponds to the axis of the top that is precessing, as the top sits on one point and precesses, then I can look at the other end of the top, and that's going to sweep out some path on the unit sphere. Very much similar to what we had before. So every point, I can take the tangent vector, and I get a corresponding point on the unit sphere. And as I move along the curve, I get a corresponding motion along the unit sphere. And as an aside, for those of you who want to dig a little bit deeper into the differential geometry, If you have two material frames that are perpendicular to the tangent vector, and the tangent vector got mapped to a point on the unit sphere, that is, it got mapped into a radius, a vector from the center of the sphere to the tip of the sphere, then where do the other two vectors that are perpendicular to the tangent vector get mapped to? Well, they have to be perpendicular to the radius of the sphere. That is, they have to be two vectors on the surface of the sphere. And when you have a vector on the surface of the sphere, you can ask, how should I slide or advect or transport that vector along some path on the unit sphere? All right? And it turns out that sliding a vector in space on a flat plane is very easy, right? I just move it here, I move it here, I move it here, everything's good. And if I come back to where I started, I get the same vector. But if you slide a vector around on a sphere or on anything that has curvature, surprising things happen. If I have a sphere here, and I start with this vector and it's pointing towards you, and I'm going to move it along a spherical triangle that looks like this. And I'm going to do it without twisting any more than I have to, because that's exactly what I don't want to do. So I'll move down here. Then I'll move here. And then I'll move here. And I don't get the same thing I started with. And that's exactly the property that says that this surface has curvature. That is what curvature is. And that's why on a flat plane I get back the same thing I started with, is because there's no curvature. In fact, you can show by Gauss-Bonnet, which is the higher order equivalent of the turning number theorem, that the angle made between when I started and when I ended is directly related to the area enclosed by the spherical polygon. So moving a vector, moving a frame here in a parallel way corresponds to moving those vectors on the surface of the sphere without turning any more than needed. And the area enclosed during that motion will lead to some change at the end. So we now have a little dilemma on hand. I said to you that when I have this shape, there's some competition between bending and twisting. Let's look at this intuitively. If I grab this guy and I start twisting, a helix forms. Now, why does this helix form? Well, one thing that this curve could do is, as I twist it, it could just stay a straight line and just store all its energy as just some twisting. I don't like twisting. But instead, it doesn't like twisting so much that it prefers to buckle eventually. And if I do this right, it prefers to buckle eventually, and it starts to make these helical things. Now, why doesn't it go just totally into a helix? Well, because there's some amount of bending. And when you go into a helix, you create bending. So there's a competition between the bending that's stopping it from going too much into a helix, and the fact that by going into a helix, it is somehow relieving the stretching, the twisting mode. So the puzzle I have for you, and that'll end the math part of the talk, which is the second time I've said this, by the way. The puzzle I have for you is, why is it that going to a helical shape somehow relieves some of the twisting that's happening? Now look at my two hands. If I start with this curve as a straight line, and I think I have a straight line so the frame looks like this all throughout, what is the corresponding picture of this on the unit sphere? It's just a point, because the tangent hasn't moved at all, right? And as I twist this, what am I doing to the material frame? I am creating twist in it. It's rotating. I'm creating some angular momentum. How can this curve reduce the amount of energy stored in twisting? One thing it could do is it could force my hand to turn, but I'm not going to let it do that. I'm going to hold these tight. So the only other way that this curve can reduce twisting energy is to move the curve, to move the center line in such a way that in retrospect, the material frames I have prescribed at both ends are closer to being twist-free. And what does that mean? Well, remember that if I have some enclosed area on the unit sphere and I move a frame all the way around in a twist-free way, I actually make an angle by where I started. So if I start with these and I make an angle between them, if there's such a way that the curve can move on the unit sphere, such as to enclose some area, then the fact that I created an angle here can in retrospect be attributed to a twist-free motion. So when I roll my hands this way, I'm asking to create some amount of area on the unit sphere. And what is bending doing? Well, bending, remember that bending, as the tangent vector changed, that corresponded to motion on the unit sphere. Remember that length on the unit sphere corresponded to bending. So reducing bending means making shorter perimeters on the unit sphere. And creating twisting means creating area on the unit sphere. So really what we have is a kind of a soap bubble problem or an isoperimetric problem on the unit sphere. We're trying to minimize perimeter of some shape while getting some area to that shape. And in general, if you want some area with minimum perimeter, what sort of shape do you get? A circle. And a circle on the unit sphere corresponds to the tangent vector precessing in a circular way. And if you spread that out over length, you get a helix. So that's the geometry for why helices form in this case. And you can understand it purely in that geometric way. So in most of my talks, you have some sort of summary that looks like this. It says, we've identified the geometry in the smooth case, and we need to rebuild it in the discrete case. And today, in the interest of time, we're only going to walk very quickly through the discrete case. But briefly, we have to have now a straight curve, a piecewise linear curve. We have to have some notion of frames on this curve. We have to have some notion of twist-free motion on that curve. And if we refer back to this picture, essentially what we have now, sorry about that, if we refer back to this picture, essentially what we have now is the competition on the unit sphere between a spherical polygon, between its perimeter and its area. So that's what the discretization accomplishes, is it's a competition between the spherical polygon, the perimeter and its area. So let's see what kind of effects you can get by using this kind of geometric model. One thing you can get is these formation of plectonemes. So as you twist this elastic rod, these helices form, and then the helices form these twisted structures known as plectonemes. And if you look at these again, you'll notice that these are actually the double helices that come up in DNA and other biological applications. And in fact, have been known to merge. These plectoneme structures in DNA have been known to merge in certain cases, and this is a visualization of how these plectonemes can merge. You can generalize the model to talk about things that don't have a circular cross-section, but have an anisotropic cross-section, and then you can get lots of interesting behaviors. Like if you have a kink, you can get twisting concentrated on one side and then hopping over to the other side. Now, one of the things we wanted to do is ask how well does this model, since it's just very simple and geometric, how well does it validate against existing results? And so we looked at a few experiments. One of them said, if you have a very long elastic rod and you start twisting it, you get a helix, but you're holding the ends fixed. So you get a helix that has small amplitude, and then bigger amplitude, and then smaller amplitude. There are analytical results for this. And that amplitude is shown by this red curve. And so we looked for various values of the number of vertices at how we approach that kind of envelope. And you converge to it very quickly. Another example we looked at is if you take an elastic rod and you close it up, but before you close it up, you add some amount of twist to it. Well, if you add very little twist to it, you really don't change its shape. But if you add enough twist to it before you close it up, it buckles. from this way to this way. And you can ask, when does that transition occur? And there are analytical results for when you transition from staying flat to buckling, and the dots correspond to simulations. So we did all kinds of validations like these. But from a graphics perspective, I think what's more fun is some of the phenomena you can capture with this kind of model. So this is one that was annoying all of us when we had landlines with curved cables at home. And it's called the helical perversion. And it's perverted because you can't get it out. So you take a helix, you pull it up, you pull it to a straight line, and then while holding the material frames fixed, you bring it back together, and you get two helices of opposite chirality. And this is actually a stable configuration, which is very annoying. This is a nice example to show coupling, nonlinear coupling between two modes. You have this thing that goes between a bobbing motion and a twisting motion. It's just a spring on a weight. And now we'll show a rendering. The rendering looks smooth, but the underlying simulation was with about 30 vertices. So it's running in real time, and it captures that connection between the two modes. So at the time we were working on this, by random chance, I was contacted by people from Adobe Research. They had just started one of the new Adobe Research units. And they said, we want to make a new paintbrush for Photoshop that's physics-based. And I said, well, that's amazing because we just developed a strand model. So now if you open up Photoshop 5 or Illustrator 5, one of the brushes in there, oh, I'm doing this only for my own benefit. Let's see. If you open that up, one of the brushes in there is called the mixer brush. And the mixer brush is physics-based, and it has all of the characteristics you'd expect: length, the thickness of the brush, and as you update them, it shows you in real time the different characteristics being modified. And you can get all kinds of effects, like if you make the stiffness really low, then you get all this fraying that you'd expect to get. So this is running with about 150 elastic rods in real time. Since then, they've optimized it further. But this isn't a commercial product. That's not a special version that I have myself. Also at around that time, so we were doing this basically as some abstract thing to just study the geometry of what's going on. But we started working with Weta Digital, and they were interested in using this kind of techniques for simulating hair and fur in various movies, and we've been working with them since then. One of Jessica's students, James O'Brien, and his peers used this elastic rod model as part of a tool that they developed. It's a wonderful visualization here, for simulating the motion of flexible, steerable needles through human tissue. So it was nice to see it get some mileage in biomedical applications. And for a long time we worked on it in the context of visual effects, and then I met a couple physicists, one of them Pedro Rice. And Pedro said, you know, this has applications in several other domains. So one of them is laying down of cables on the ocean floor. So the only reason we have an internet connection with Europe is not because of satellites, it's because somebody bothered to put down cables on the ocean floor. And they have these big ships, and the cables wrapped around on the ship, and this ship is moving along and dropping the cable down. And another application which is relevant is at the other extreme, the other end of the scale. For nano manufacturing with nanotubes, you want to make stretchable electronics. How much time do I have?
10 more minutes.
10 more minutes. Okay, let me know in 5 minutes. So, so you're laying this down, and you want to make stretchable electronics. One of the tricks with stretchable electronics is you don't want your wires to snap. If you don't want the wires to snap, you need some way of laying them down so that they have some give. They have some sort of zigzag pattern. But you don't have little tiny printheads for doing this, so you need some sort of passive effect that creates this, such as dropping this spaghetti at just the right rate so that as it falls, it makes some sort of sinusoidal pattern. Also, with the ocean cables, laying down the cables on the ocean, you don't want some shift in the ocean floor to snap these cables. So you want them to have some give. So you want to lay them down in a kind of sinusoidal pattern. But you want to be able to control that pattern. If it's too sinusoidal, you're wasting cable. If it's too straight, you're too fragile. So Pedro put together some experiments in the lab for what we call coiling spaghetti. And here's a spaghetti coiling, and there's just the parameters, the speed of the belt and the speed at which you deposit. And really, the only important parameter here is the difference between the speed at which you deposit and the speed of the belt, this epsilon. And we're assuming that epsilon is always positive, meaning you're always dropping the cable faster than the belt is taking it away. If the belt's moving really fast and you drop it slow, you're getting the cable dragging along, and that's not the case we're interested in. So you can talk about lots of different experiments that can be done as a function of epsilon. I want to tell you about one anecdote here in which simulation made a big difference to our scientific findings. So Pedro was doing these experiments. Let me go back. Well, I'm just going to say it in words. So Pedro was doing these experiments where he was just dropping the spaghetti on the floor, and he was noticing that as the spaghetti falls, every once in a while, it starts inverting and turning in the other direction. All right? So he said, let's validate against our code, and we could not get that. Our spaghetti was always turning in the same direction. And we went back and forth and matched with him over and over the Young's modulus, the height, the thickness of the cable, everything. And we said, is there anything we could possibly be overlooking? And my student John Suk said maybe the natural curvature. So sometimes these rods have some natural curvature to them. They're not perfectly straight. See the tip, for example. And Pedro said that effect shouldn't matter in this case. And John Suk gave up and went to Weta Digital to do movies, which is easier to do. And then when he was there, he decided to just fiddle and put in natural curvature, just a parameter in the simulation. And as soon as he put in some natural curvature, sure enough, it started alternating directions. And so he just played just with the natural curvature as the only parameter and matched to the rate of inversion in the video. And I have this email where we sent an email to Pedro from New Zealand to Boston saying, by any chance, are you storing your cables on a spool of such and such diameter? And he came back and said, you guessed it within 2%. That's an example where a geometric effect is really important. And what's interesting is that 2 years later, he still hasn't been able to manufacture cables that are perfectly straight and long enough to run the experiments. See, the cables, in order to be shipped, have to be rolled up, and then plasticity kicks in. And if they're too short, you can't run the experiments. He can verify now by looking at trends that, in fact, the natural curvature makes a big difference. But you can understand that if this inversion is a function of the natural curvature of the curve, then if you have these ships that are deploying these cables, and the cables are all stored in a spooled fashion on top of the ship, then that's going to affect your model for how the cable is deposited. And since then, we've done a bunch of experiments, like the rate of inversion compared to the injection height, and we've matched experiments to simulations. And I don't really have time to talk about all these right now, but there's a bunch of results relating to this project.
Just before you leave this, so you were saying that the twisting versus bending, there is an opposition. So could you store the cables by twisting them?
Those are exactly the sort of thing. So the way our process is working is first we're trying to understand these phenomena, and then we can try to combat them. So we can talk about having twisting of the nozzle heads or some other sort of thing like that. And that's exactly what we're looking at right now. So we think yes, but we're not sure. So since I have to wrap up soon, I just want to say that there are other things that we're doing in graphics that are really important for the sciences. One of the projects we recently did for SIGGRAPH is one on interactive design. So on the left side of the screen, you see the flat patterns from which a textile is cut out. And on the right side of the screen, you see a simulation that's done in real time. So every time the pattern is modified on the left, you get an instant update for the simulation on the right, and you can dress the armadillo. So in the project with Pedro, that's exciting because that means that now you can have these simulations running and do sensitivity analysis. As you modify things like the height or other aspects of the geometry of the experimental setup, you can immediately get results in a way that's extremely tedious if you're working with a physical apparatus. So the technologies that we developed there for kind of interactive design can carry over as well. Adrian? Okay, cool. So just to briefly talk about another related physical phenomenon, if you can do falling spaghetti, a very related phenomenon is honey falling. And that's this kind of notion of liquids falling and behaving like ropes or like solids. Here's lava folding, for instance. Is also important in lots of manufacturing applications. For example, 1/3 of the textiles produced in the world are non-woven textiles. They're created by having molten polymers inside a drum, and the drum is spinning, and the drum has little holes in it, and this polymer is spewing out, and it's drying up as it's spewing out, and it's hitting some platform. So Stephen Morris at the University of Toronto conducted these experiments, which he called the viscoelastic sewing machine. And the idea is that there's just honey falling onto a moving belt. And the nozzle isn't moving, the honey is being deposited at concentrate. The only thing that's being varied here is the speed at which the belt is moving. And just by changing the speed of the belt, he can get a whole bunch of different patterns for the sewing machine, which I think is really great for decorating cupcakes. But again, it has applications to stretchable electronics and so forth. So a lot of the technologies that we've been developing for, I think I'm going to skip a couple slides here. A lot of the technologies that we've been developing for elastic rods can carry over pretty much directly to doing these kind of viscous, gooey threads of liquid. And so here you have a simulation of the sewing machine, the viscous sewing machine. And we're able to recover many of the patterns. There are a couple patterns that we can't recover yet, and we think that's another interesting story, like before, that if you don't account for certain phenomena, you can't get certain effects. And as we learn to account for them in the simulation, we will gain understanding for why those effects happen in real life. So of course, if I'm going to talk about scientists, here's a picture of some of the scientists. One of these is not a scientist I work with. All the others are, so I'll let you leave your guess about that. So recap, and I'll end in 2 slides. So the idea is identify some geometric structure, carry over that structure from the smooth case to the discrete case from first principles, and get cool results. Right, this is fantastic. So if this agenda works, then all we have to do is preserve all relevant structures. So that would be nice. The question is, can that be done? And the answer is, can be summarized by this one project here, which is consider some very simple fundamental sort of operator that's used all over in geometry processing, vision, computer graphics, and that's Laplace operator, Laplace's equation. And if you open up any textbook, you can get a whole bunch of properties for the Laplace operator. And if you look at these properties, which are shown as columns here, and you do a literature review, and look at which of the operators, finite elements, graph Laplacians, and so forth, preserve which properties, you get this conspicuous diagonal of missing properties. So it seems that every element that's out there, every discretization that's out there, seems to be missing one of these fundamental properties of the smooth Laplacian. And is this a coincidence? And the answer is no, there's no free lunch. We can prove that if you take an arbitrary triangle mesh, you cannot design a perfect Laplacian, that is one that preserves all geometric structure. Which means we're in business forever because each application requires that we seek the relevant structure and carry over that structure to the discrete case. So with that, I thank you very much for your attention. Yeah.
Are there any of these?
What's your name?
Colin.
Colin.
Colin Otis. Yeah. Are there any of these things that you showed that you can't capture the physics with traditional numerical?
That's right. So, I'm going to answer an opposite question. There are lots of things I can't do with this method, and then I'll tell you what I can do. So, everything that I showed to you relies on understanding the geometry of the problem. There are some physical systems whose behavior is not governed by geometry. It's governed by really interesting relationships between stress and strain, really interesting material behaviors. For example, if you put cornstarch in water, it has this amazing effect where you can run over the pool of cornstarch in water, but if you stand in one place, you sink. In other words, it's a material that behaves like a solid at high velocities and behaves like a liquid at low temporal frequencies. That's not a geometric phenomena. That's a very, what we call a constitutive phenomena, or something to do very specific with a material. So that's not something that we would approach with this method. On the other hand, for phenomena that are highly governed by geometry more than anything else, one of the nice things about approaching it with this approach here is that you do not have to worry as much about, did I get the stress-strain relationship right? You're focusing more on, did I get the geometry right? So what you can do with this method that you can't do with other methods is, for a limited class of phenomena, you can have far simpler codes that are far faster, but just as predictive, if not more predictive.
So just a clarification question. You were talking about stretchable electronics, right? And you showed the belt that is moving. So the velocity of the belt, you're saying, is related to the curvature of a static object. So you, for any shaped electronics, you create the same simulation as though the flat belt is moving. You're saying it'll work for. Now, there's a bunch of people who...
I don't think I followed. Were you comparing the viscous case to the elastic case?
No. Just
you were saying that it doesn't depend too much on the material property?
Right. So if you had just the wire, but you showed the conveyor belt that is flat, but it was moving at different rates. Now, is that equivalent to a static object with curvature?
Oh, that's an interesting question. I don't know the answer to that. So you're saying, if I gave, I see what you're saying. You're saying, I think what you're saying is, I gave this analogy between the elastic rod and the spinning top.
Right.
Is there an equivalent analogy here between the belt, the dynamics of the belt, and some static object? No, I don't think so, because the case of the belt involves contact, and that makes any simple analogy really hard to work with. It may be possible that there is some complex analogy there, but it's not going to be something as clean and simple as Kirchhoff's analogy.
So the reason I was wondering was if you actually design stretchable curved electronic devices, like cameras or light sources and so on, how would you simulate how to lay out your wires? Because you need some extra length than just the straight thing.
Well, you wouldn't do a dynamics problem. You could use everything that we discussed about the elastic forces here, but you could put them inside an optimizer of some kind. So you don't have to, this derivation that we talked about, competition between the perimeter and the area, that doesn't have to be rolled into something that has inertia and dynamics. You could incorporate that as a prior inside some optimization problem. You could incorporate that in some other way into an optimization or statics problem. Cool.
All right.
Thank you very much.
See you.